Hi everyone, thanks for joining for this talk. I'm Ayush, a senior machine learning engineer at Pinterest. In this particular talk, we would be going from the journey for scaling ads ranking at Pinterest from very simplistic logistic regression to more complex transformer-based models. We would also be covering how natural language processing techniques and advancements there are shaping the recommendation world. So before that, just a recap what Pinterest is. Pinterest is a visual inspiration engine. Our mission is to bring everyone the inspiration to create a life that they love. This is like how you can interact with multiple touchpoints on the Pinterest ecosystem, starting from home feed, search to related pins. Let's see what Pinterest is just to give an idea about the recommendation challenges. Like Pinterest, this is my home feed, which is like a personally curated page of visually inspiring pins. Here, this is built upon my past interest and engagements in my history. Here also you can see the search tab on the page. Here, if you want to search based on any textual or visual based queries, you can do a search query. Let's say if you're interested in a particular pin, you can click on it. And once you click on it, you're also provided with many visually similar related pins experience. One thing to note here is like at Pinterest, we have a very rich corpus of images, text, which are backed by user created pins and boards in general. Now let's see how ads fit into this ecosystem. Ads are promoted by content from our advertisers. Ads help to connect users with the relevant content and take them from their inspiration to action journey. Just before that, let's look into some of the characteristics of the Pinterest recommendation system. This recommendation system to be performant need to sift through billions of content in a very low latency around 200 to 300 milliseconds. It needs to be performant, real time, and also be responsive to user feedback and also their changing preference. That's where the recent advancements in natural language processing are coming into picture. It also embraces multi-objective optimization to satisfy the optimization goals for Pinterest, for our partners, and our pinners. Also, let's look at how ads product work in general, in a very nutshell in general. Like to satisfy and to bring users the right relevant ad content, Pinterest provides a performance ads product. Advertisers can have different marketing goals in mind. It could be as simple as awareness to create brand awareness, or something that drives more clicks and engagements on their platform, on the pins on Pinterest platform. The advertisers can then also choose how they want to spend budget. It could be as simple as like a max bid and or an auto bidding product. Then they can choose different creative types. Now, to bring these products into production and to the users, we need to understand in every context that the user is in, like what is the probability of a click event. So these predictions are being based on machine learning models in general. Now, in just predicting for clicks on the platform might not be the most relevant. We also need to capture the user intent and how good is the new prediction or the new content for the particular user. And that's characterized by other supplementary labels like good clicks, height, saves, and relevance. For each of these objectives, we have a machine learning model that makes these predictions. Furthermore, like just driving engagement on the platform might not be the end goal for all advertisers. They might also want to drive users onto their platform and do more downstream activities like conversions, like checkouts, and that's another prediction model that you would need. Now let's see how this product grows if you're creating new creative types like videos. Collections. Now, if you want to make these new products and new creative types, not only we need to be able to provide all of these predictions that we have, but also we need to provide new video view predictions. Now, if you look at like these, for every of these use cases, we need to have different kind of models that can bring these performance predictions. Apart from that, Pinterest also has three heterogeneous surfaces: home feed, where the user has a past engagement or interest as their context; search, where there's a search query as a context; and then related pins, where we have an image as a context. Now, if you look at this, like spread across all of this heterogeneity, what we need to do as we grow the product is to make sure that we are able to manage the product in a linear manner and not grow exponentially. Now, also let's look at briefly about how a typical ads delivery funnel looks like. A typical ads delivery funnel has many candidate generator, which swifts through this billions or millions of content in general, trying to find the best relevant pool of ads that we can show to the user at this point. These could be as simple as generating fresh content, looking at the user's recent interactions, or embedding based generators. Their main motivation is to return the maximum set of best candidates that we can show to the user. Then this pass through a ranking model, which tries to make precise predictions for all of the use cases that I had shown before. Once we have the ranking of the ads with precise predictions, these are then passed to the auction and allocation phase, which also involves many other business logic in general before trying to find whether it's appropriate to show a particular ad to the user in that particular context. So all of this together brings the best experience on the platform. Now, the focus of this talk is the ranking model, and we'll go into some of the details about how this ranking model evolved over time. Starting in 2014, the first ranking model was a very simplistic logistic regression-based model. This is a linear model. At this point, you can imagine that ads inventory is simpler. We don't have that many features. We don't have that many data. So a very simple model is the first model to bootstrap the systems. After that, in 2017, like Pinterest moved from this linear model to a nonlinear model, which is a hybrid combination of gradient boosted decision trees and logistic regressions. This comes from a seminal Facebook paper around the same topic. The idea here is very simple. Sorry. The idea here is very simple. The gradient boosted decision tree is trying to learn nonlinear feature interactions. These features are then passed as like to train a gradient boosted decision trees. Once you have trained these trees statically, you pass them as feature translators to a logistic regression model. Now, the leaves of your gradient boosted trees are as features into the logistic regression, and logistic regression can also input other features with have high cardinality, and then these are trained together to predict the final prediction. One thing here is the GBT models here are for learning nonlinear transformations, while logistic regressions are learning some ID-specific features. To give an idea what ID-specific feature means, they are like advertiser ID, pin ID, or campaign ID in general. One thing to note for ads in particular, like ads inventory keep on changing. Like ads inventory is not static, and since it keeps on changing, we need to make sure that our models can incrementally train with new data. Here, the GBT models are trained in a batch fashion, while the logistic regression are trained incrementally to capture the changing feature distribution shifts and the new ad creatives that are created on the platform. One thing to note that in this particular world, like Pinterest was training in a hybrid and a mixed world of different languages, like this was around 2017. So these models, like GBTs, were trained in XGBoost library, while the logistic regression was trained in a TensorFlow library. But eventually, these were being served through a Pinterest internal C++ serving system. So now this kind of a hybrid system slows down the efforts in the future, and we will show some of the reasons like why we moved to native serving in the end. The other thing is these models like led to explosion in general, since as the product was growing, we have different creative types being created, requiring us to have different prediction types in general. So at some point, we had about 60 plus models to maintain, which were leading to super long cycles for feature addition and deprecation. So if we need to add a feature to a particular model, we need to spend training all of these 60 models in general to bring that power to all the entire system. Moreover, the GBT models here were static, which were not able to capture the changing feature distribution. This was all leading to like suboptimal systems, both from a maintenance perspective, but also from a performance perspective. Going forward, the next set of iterations like in the industry were around like moving from like these simpler GBT models and logistic regression to more neural network based models. As you can imagine, like neural network based models are universal approximators. They can look at the history and try to predict the future. So that's the direction we want to go, because now you can learn many different combinations that you're not able to learn in the prior setups. Just before going there, some of the logical reasons why moving to DNNs makes sense here is, one, DNNs bring a lot of more power, which the other models don't have, like specifically learning feature interactions, utilizing pre-trained embeddings from the model, or learning embeddings as part of the model itself, and also moving to more sequences. Sequences is taking the inspiration from the NLP domain in general, and how having sequences in the model would help drastically, something I'll cover in a later slide. This is the motivation of the simple model of what the DNN plus logistic regression model looks like. Here, instead of having a GBT, which is trying to learn the feature interactions, we have a DNN simple machine learning layer perceptrons, which are trying to learn this interaction. And once we have learned these interactions, these are then concatenated with our logistic regression models that have the ID features in them to learn a performance prediction. One thing to note, the ID features usage in the models help us to learn some specific characteristics that are limited to a particular advertiser, and that's how we can control the diversity between different advertisers and their content. One thing, like at least till this point, like traditional machine learning was relying on like handcrafted features, utilizing context features, engagement features, content-based features, and impression features. But these are all handcrafted, and learning feature interactions, like what kind of two features do you want to cross together, or those kind of nonlinear interactions, but also designed by hand. As the system started to grow, we realized that this handcrafted feature engineering is not scaling up well. So the next set of iterations that happened were to improve this handcrafted feature engineering and let the model learn this feature engineering. So this is like where Pinterest deep multitask neural network based model came in around 2020. So now this relative red boxes are the relative wins that we see from each of these iterations. So if you look at from 2017 to 2018, moving to deep neural networks might not have given that much big gain, but it sets up for success in the future. And then bringing the first DNN-based multitask model took us even longer, but the gains were much higher. This is because we were re-architecting the stack during this time to prepare for more wins in general. So this is the Pinterest AutoML in nature. Like this is what the architecture has at a very high level. So one of the main benefit of this model is that it can take raw features as input. So taking it from like moving away from doing feature engineering by hand, this model can just do feature engineering as part of the model, learning feature interactions through different summarization and latent cross layers. And further, we could also multitask these models with different objectives that are correlated. So this brings in like more power to these models to be co-learning and utilizing transfer learning capacities. So this is like a very high overview of this model in general and what different layers it has. Like the first layer is the representation layer. This is like similar to any other machine learning, like deep learning based models in general. Specifically for deep learning models, like feature representation and pre-processing is really important, unlike the GPT words. So this is like the interface between the raw features and then passing it into the model before further processing. So here we have notion like if the feature is a categorical feature, you can have squashing, clipping, hashing, normalization, and other kind of feature processing. For categorical features with low dimensionality, you can have just vocabulary and learning and embedding, or you could have like learn also a hashing-based representation. Then also we had a notion of summarization layer. This takes in the knowledge from the previous world that we want to handcraft features together. So here we could define two features to be learned together in general, such as like category vector for a user and a pin. And these features like category vectors or annotations are coming from a natural language processing understanding of the pin and the user in general and what they have interacted with. Going forward, we tried to reduce the reliance on this summarization layer because it was still a manual and crafted nature to decide what features need to go together. The next layer that we have here is the latent cross layers. These are multiplicative layers with very high degree interactions which are forcing explicit feature crossing. This could be similar to any of the architectures in the industry like DCNV2, low-rank DCNV2s or MarsNets. These are then passed to fully connected classic deep learning based neural networks. Now, this is like a single task models that I have shown before. Now, as the product is growing, how can we make sure that we can train these models in a scalable way? That's where we could multitask these models, not only help to learn from denser labels to sparse labels, but also utilize learning from cross-domain interactions. Here in this model, you can see that the backbone that we shared before, that could be a feature representation bottom in general. Latent cross layers are trying to learn different feature interactions. Now you can use those feature interactions to fine tune your different objectives in general. So here also we had this notion that we can split the part of the network based on based on intuition. For Pinterest, we have two heterogeneous surfaces like standard ads and shopping ads. So here we split the network parameters at the top layers differently so that we can better control the sharedness and sampling techniques. So this was before like more research into the industry in this direction, but now we have more fundamental ways to do this kind of distinction through models like MMOE and PLEs. But this is the time when it happened before that in general. So this was like till 2020, Pinterest was still focused on improving the model architectures and preparing the stack for the further advancements that we had planned in the future. The next step here is the attention sequence. Like attention, like now we want to not just utilize the features that the users are having at that particular time, but we also want to understand their prior history on the platform in general. And that's the motivation from where the natural language advancements get connected to the recommendation systems. And I'll go into some of the details here as part of this talk. So the first here is like, how can we understand the journey that the user does on the platform? So now if you look at a user interacting with pins on the platform, they have a journey. They might interact with different kind of and diverse kind of set of pins. They could be as simple as recipe related pins, furniture related pins, or travel related pins. So the main motivation here is how can we understand this journey? We present this as a native in a very latent space and then try to understand what the user is going to do next and how they are going to interact on the platform. So if you can imagine, this journey can be treated as words in a sentence, and how do we want to learn on top of it in general? Before we go that in general about the attention sequence, let's understand like one of the very fundamental embedding based generators, like embedding based content generator that we have in the platform in general, the PinSage embeddings. Like Pinterest has a published paper on the same, but what this tries to bring is that you have content based, very rich engagement based signals. It uses different modalities. It's a multi-modality learning based on graph based systems. Here you is trying to get a feature representation for a particular pin by looking at its textual representation, looking at its visual representation, and also how users interact with particular pins in a graph-based manner. Once we have this, these are very rich representations, and I will show how in the future slides this fuels majority of the recommendation system power in the system. Now let's go back into the attention model and the journey that we showed for a particular user. Here we have different pins that are being interacted in the journey. But now let's say if we want to have a target pin where we want to have a prediction. Not all of this part of the journey is relevant to the prediction at that point because some of them might not be very relevant, such as like the furniture or the travel. So we utilize an attention-based mechanism instead of just mean pooling here to understand which particular pin should we pay more attention to. In this particular scenario, we need to pay more attention to the first two pins, and that's what is the representation of this journey in this context. And the representation of the user journey can change in the context, and that's where the attention model comes into picture. One thing at this point, like Pinterest models are still serving in CPU, so we want to make sure that this computation is simplistic in general. To make sure that it's low latency, we can only restrict it to short-term sequence histories in general. So something like 8 past histories or 16 past histories or engagements of the user. We also utilize pre-trained embeddings coming from our PinSage space in general because they are very rich signals, and we can now do content-based recommendations in general. We also introduce simple machine learning MLP-based transforms in general, which are also very similar to other techniques that are being done in the NLP domain. This helps us to control the output dimension and also introduce non-linearities that are learned as part of the model in general. So going forward till this point, we could see that having sequence is very crucial to improving the responsiveness of the model on the platform. But at this point, if you can see that like Pinterest was still relying on the hybrid system where we are training a model in TensorFlow, but we are using an inbuilt house library called as Linchpin for serving these models. And one of the reasons for that was that our in-house library was very optimized. But now as the model architectures and systems became more complex, it became much harder to have the same kind of translation between training and serving. So the next step of improvements that went into the system was to ensure that we could have native TensorFlow serving on the platform so that we can prepare for further advancements in the next directions that we wanted to plan. The next set of improvements that came in was a transformer-based sequence in general. Instead of relying on attention, can we move to more transformer-based sequences? And I'll go into some of the details there. Transformer is like kind of a Pareto optimal solution in the current machine learning pipeline. Transformers can encode many different kind of feature interactions in general. So we wanted to increase our feature sequence beyond the last 8 or 16 items that we had to something like 100 plus user events in past 3 months. So this could capture even more long-term sequences in general. But now since we're limited by GPU serving, we cannot have complex features in this particular scenario. So in terms of features, the features were very simplistic, such as categorical features that are like something like pins annotation types, the action that the user did there, and also we introduced the timestamp related features to capture the time relatedness in general, like was it just a day before or something that was like a month before that happened in general. And adding this time awareness to the model also made great improvements to the model performance. So at this point, we had established that having a longer term sequence is even more powerful than also keeping both the longer term and shorter term sequence is more powerful in general. So now the next set of iterations that happened was like, can we make this long-term sequence more performant by having more content-based graph-based embeddings that I had shown before? And that's where our recent work around pinner former comes into picture. So pinner former is a personalization of like understanding of the user in general based on their sequence. This is a published paper from Pinterest. If you're interested, please go give it a read. Here, we look at the user's activity sequence, not in the simple categorical features, but more about these graph-based embeddings that we have, and trying to capture it using a transformer-based encoder into a user-based embedding. And the objective here is trying to predict what is the next interaction that the user is going to do. And there are many more details into this implementation. Please feel free to read our paper. Once we have this spinner format, which is a user representation spanning more than 100 events, like around months in general, we can have a better, rich representation of the user on the platform that can fuel all the downstream applications. In all the downstream applications, this feature was very important since it has multi-months of data and understanding of the user. Now you can look at how we can combine these different like long-term sequences and also the real-time sequence in a manner that we can serve these models in general. If you look at the pinner former is looking at more long-term sequence. This part of the model that we have in the transformer-based sequences can be learned prior to create a user embedding and embedded in an offline manner, and which can be used to serve in general. Since this can be done offline, all of this computation, this can be easy to compute and use as a user feature during the serving time. Also, since the power of having a real-time sequence and how people evolve, we can also have a real-time sequence that is co-training as part of this model in general. To bring different kind of content-based embeddings into the system, we can also introduce GPU learning so that we can learn complicated feature interactions here with more parameters. So this was the journey of Pinterest in general, how natural language processing, starting from like sequence modeling, has dominated and motivated the iterations that we have specifically around the transformer sequence and usage of transformer-based models. So in this particular talk, we mostly discussed about the evolution of the model, how the model architecture evolved, and how different components of like sequence modeling is influencing the recommendation stage. But also, this is like very tip of the iceberg that I shared here today in general. Like, as you know, that empowering web scale machine learning is very complicated. So this is like a very small piece of the puzzle, like how you're doing this architecture in general. But to bring these advancements to production, we need a very good bunch of suits that work in parallel in general. So during this time, Pinterest spent a lot of time to improve all of our machine learning platform capabilities and all of the auxiliary systems so that we can bring this experience to the users and pinners. I also want to take this step to acknowledge the vast cross-functional collaborations into every team in the company, including many different teams, to bring the best experience for the users and pinners on the platform. Thank you for listening.